Just as we described previously, we can think about the movement away from set point. So when we receive the stimulus here, this is our threshold value of -55. As soon as we get to that -55 millivolts, we're going to open up voltage-gated sodium channels. Sodium is going to diffuse into the cell. Rush is the word that I like here because it has such a strong current. And then what happens is this is going to result in more depolarization. So more depolarization actually further potentiates or opens up more sodium gated channels. So this is what we mean by this being a positive feedback. Remember, positive feedback facilitates moving further and further and further away from set point. So essentially, as we depolarize the membrane and as the sodium channels on the membrane experience the sodium rushing into the cell, it just further facilitates the opening up of more sodium channels, which is why this ends up being such a rapid upstroke in the membrane potential because that is being regenerated. Okay, this is a process that we call regenerative. All right, regenerative, which means that it's going to further potentiate the opening of more sodium channels. Now, if we think about the opposite movement, so as soon as we get back to positive, or excuse me, as soon as we get to positive 30, so we go from -70 at -55, begin depolarizing, and then we go all the way up to positive 30. And then at that time, we have a reverse in the state of our channels. So now we end up seeing the closure of sodium channels, the voltage-gated sodium channels, and the opening of potassium channels. This is also voltage regulated. So at positive 30, these potassium channels will open. And now we're going to see potassium leaving the cell according to its electrochemical force. And that is going to result in less depolarization, making this a negative feedback example. Okay. All right, now we're going to go through and explain this, and the perspective that we're going to explain or describe this from here is thinking about the permeability. So we want to think about what does the permeability look like for sodium and potassium, and how is that changing alongside looking at the events of the action potential. So we want to first begin by saying that there's a greater permeability for potassium than for sodium. We know this, right? We've said this before. We also want to say that because of that greater permeability, there is, when the membrane potential is at rest at -70, it's actually closer to potassium's equilibrium potential, which is -94. So because more potassium channels are open when the membrane is at rest, the resting membrane potential looks more like potassium's equilibrium potential, which is negative. But it's really far away from sodium's equilibrium potential, which is +60. Okay, so that's going to tell us where the membrane is at rest, what the channels look like, the fact that there's more potassium channels open and fewer sodium channels open, but that is also going to tell us the magnitude or the strength with which these ions are going to move when additional channels are opened up. So because potassium is close to its equilibrium, its movement is going to be slower. And because sodium is far away from its equilibrium, its movement is going to be faster. So when we begin the action potential, right, we have sodium channels open up, and the purple curve shows the permeability to sodium. So as sodium channels open up, then we have a rapid increase in sodium's permeability. That is going to correspond with the depolarization phase of the action potential, right? This rapid upstroke here. Now, as we have the change of events which occur at +30, this prevents the membrane potential from actually arriving at sodium's equilibrium potential, which is way up here at, let's say, positive 60, right? Somewhere around here. So it never actually gets to positive 60 because of the membrane potential changes that are triggered by the potassium channels opening up and sodium channels closing at positive 30. So these events are triggered here, which results in a downward slope in the membrane potential. But as we're doing that, we can see that sodium's permeability is also decreasing. However, potassium's permeability begins to rise at positive 30. So potassium's permeability rises, and then that is going to slowly drop as well. But what I want to point out here is that when we get to the resting membrane potential, we never actually get back to rest. So this is where we're trying to aim to be at, negative 70. We kind of overshoot the resting membrane potential. So this gets a little bit lower at about negative 85 or so, because potassium is still moving. If you look at its permeability, potassium channels are still open and potassium is still moving. So until all of the potassium channels close, which is about here, then we can have the sodium potassium pumps be engaged, and that will bring us back to our resting membrane potential. Okay. So just to kind of review that in a more summarized way, we have weighted potentials that bring the membrane to threshold, which we said is negative 55. And then we have the rapid opening up of sodium channels. Remember, we described this as being a regenerative mechanism because the more sodium channels opened, the more additional sodium channels were triggered to be open, right? Because remember, they're voltage dependent. So if I open up one sodium channel, right, these are along the length of the axon. If I open up one, sodium can rush in. It's going to be more favorable for the adjacent channel to open up because I've depolarized that segment of the membrane. And then if I open up another one, the other one will open up because more sodium has rushed in and has increased the membrane potential. So this is going to further potentiate this very quickly, and we have the upstroke of the action potential. At the positive 30 mark, we have two things happening. We have the closure of sodium channels. And just to be more specific here, this is the inactivation gate. Okay, the inactivation gate on the sodium channels specifically are going to close. Remember, these are only open for 1 millisecond. So as soon as that membrane depolarizes, a 1 millisecond timer goes off, and by the time we get to positive 30, the inactivation gates are closed. Also happening at positive 30 is the opening of potassium channels. So that completely reverses the membrane potential. Sodium channels close, potassium channels open, and now we have a shift, a complete 180 shift in the direction of the membrane potential change. All right. And then the opening up of potassium channels and closing of sodium channels is the reason that the membrane potential, or the action potential rather, doesn't actually arrive at sodium's equilibrium potential, which is way up here, but it's trying to get there. That's the purpose of moving sodium, rushing sodium into the cell, is sodium is trying to achieve or arrive at its equilibrium potential, but because of the gating mechanisms in place, it doesn't ever arrive at positive 60. Then we have potassium's movement. So potassium channels remain open beyond the resting membrane potential. Again, focusing on the red curve here, which is the actual action potential events. Notice that this goes down past negative 70 and goes slightly lower than negative 70. And this is because potassium is still leaving the cell because its channels are still open, right? It's still slowly closing those potassium channels. So the membrane potential in this instance tries to arrive at potassium's equilibrium potential, which is negative 94, okay? It never actually gets there because all of those potassium channels end up closing before we get as low as negative 94. All right. And then we have the sodium potassium pumps, which are engaged as soon as all of the potassium channels close. About here or so, we have the sodium potassium pumps, and they are going to reestablish the resting membrane potential, right? So if we look at this more holistically, okay, we have the same set of events. I feel like I'm being very repetitive and going over this in many different ways, but this can be a very abstract concept to grasp. So I want to try to explain it from several different perspectives. So phase one is our depolarization, which is movement of sodium. Phase two is our repolarization, which is movement of potassium. Here's our threshold value, negative 55. This is what begins the entire chain of events. And then here is our overshooting the resting membrane potential, where we go below negative 70 to about negative 85. And then we slowly reestablish the resting membrane potential. Now, when you think about the action potential, we need to describe the all or none principle. This is governing the magnitude, duration, and whether or not we actually fire an action potential. So the purpose of the threshold value, right, negative 55, is that this is all or nothing. Either we're going to have an action potential or we're not, okay? We don't have half of an action potential. We can't partially have an action potential. It's either a full action potential or none at all. And so negative 55 is the minimum depolarization that's required to begin the chain of events that will open up all of the sodium, the voltage-gated sodium channels. Now, let's say we had a different size of stimulus, right? A different size of graded potential. If it is a threshold depolarization, we're going to fire an action potential. If it is a sub-threshold depolarization, let's say it only got to, I don't know, negative 60. It didn't quite get to negative 55. Then we have no action potential. Even if it got to negative 56, right? If it wasn't negative 55, there's no action potential. Let's say we had a really strong stimulus that took us past negative 55. Let's say it took us to negative 40 or negative 30. We would still have the exact same amplitude and duration or action potential. Okay, so the action potential always looks the same. It's identical, even if we have a strong stimulus or just at negative 55 still stimulus, it's going to be the exact same action potential. All right, so the magnitude is always the same. It always goes from negative 70 to positive 30, and then back down to negative 85, and then correct to negative 70. Now, when we think about how we can send different type of signals with the nervous system, we want to think about the frequency of action potentials. So the way that the nervous system sort of separates or grades different types of stimuli, right? Let's say I want to move my arms. I want to make a small movement. It's going to result in a small number of action potentials, maybe 3 or 4 action potentials. Let's say I want to make a larger movement that's going to require more muscle contraction. The way that that is communicated through neurons is to generate more action potentials, maybe 10, 20 action potentials. So the way that we can sort of begin to separate and grade different types of stimuli is by the frequency of the action potentials and not by the size or strength or duration of the action potential, because they are always the exact same in terms of those factors. So just to kind of reiterate that example here, if we have a weak stimulus, same action potential, same size, same duration, same magnitude. If we have a medium stimulus, same. And if we have a strong stimulus, the exact same. Okay. All right. And then here as well. So here's our graded potential, which is a sub-threshold stimulus. Here's another slightly larger graded potential, also a sub-threshold stimulus in that it's not enough to get us to -55. Now we have a threshold stimulus. So that gets us to -55 and we fire the action potential from -55 to +30 and back. If we have a large stimulus, even if it were twice as large as the threshold stimulus here, it's still going to generate the exact same action potential. All right. And as I mentioned before, the way that we do signal an increased stimulus in the nervous system is by having multiple action potentials, which is indicative of a stronger stimulus versus one or two action potentials, which is indicative of a smaller or lower signal.